G'day, Lance from Motive Power, back again. And today we're talking about tipping things over. How do you stop your loader or your crane from making a very big embarrassment? So we're going to talk about tipping and rolling over. So to date we've looked at the ground interface, the support and the configuration of the vehicle. We've talked a little bit about stability in the level and on the grades. But we're really today going to talk about tipping things over. It's obviously a big drama. It does happen. It happens quite a lot. And it's mainly a concern with vehicles carrying overhung loads. Now that's cranes and loaders and the like. It is an issue with other vehicles, but those two are probably the worst case, and we're going to use them as examples today. Part of your design process will be to determine whether there is a load condition, an application condition, a configuration where the vehicle is going to be vulnerable to rolling over. And it's not always applicable to the perfect situation. You may have worked out the grade is a simple 1 in 4, and you know your vehicle's stable on that. But what happens when one wheel goes into a pothole at the wrong time? Or maybe another wheel runs over a rock at the wrong time? You're affecting your stability. And a flat tire will also cause you grief as well. This sort of review can lead to questions like, how do we reduce the possibility of rollover or tipping? And that might lead you into other systems. For example, you might want a crane to be interlocked with stabilizers so that you can't carry the load, you can't lift a load beyond a certain point unless the stabilizers are engaged and the vehicle's in neutral. So you can't think about this in its solely as one subject. It does link to other aspects of the vehicle. So why all this focus about stability? It's because in the real world, things like this happen. Now, I doubt that many of us really have to worry about what load we put on the donkey, but this is a silly example of why. A more serious example of why is this. Cranes do fall over. And then we get things like this, which is a fairly recent example in our local area. If I had to guess, he had half a bucket on one side and steered and it tipped him over. He's on a grade, but he's actually pointed down the grade, which would have been a better situation. So obviously things like this do occur and you have to be prepared for it. And the equipment needs to be prepared to minimize the risk of this happening. There are standards for stability for a lot of vehicles. I have difficulty sometimes underground where so-called loaders are actually tool carriers and carry man baskets, and sometimes things don't quite fit into standards, but there's a pretty good array of standards that you can apply, particularly say ISO 14397. Cranes generally have pretty good indications of their capabilities. Their specifications are usually well set out, but again, they are in defined applications. Let's look at a quick example. Okay, here's what used to be a DMAG crane, now Tadano, and it's a big fella. This is their spec sheet. I'm going to go down here and we're going to look at how well defined it is. So typical crane, capabilities 360 degrees with different booms, different boom angles and so forth. Well defined for any normal crane. Cranes also have graphs like this, quite common. You can work out what the crane is able to carry at certain loads. And a lot of cranes are also pick and carry, where they can pick up stuff and move it around. Not so much in the big sizes. One of the issues with cranes, particularly using stabilizers for stability, is can the ground support the stability, the forces from it. It's also an issue with elevating work platforms, where the standards require you to actually say what the ground strength needs to be. This is a little bit out of the Tadano manual, and you'll see this is about outriggers, 179 and 197 ton. So your ground conditions need to be able to support that. If you're actually on the ground, that can be fairly well determined. But I have seen a big crane go over because it was working on the top of a car park and the outriggers punched through the concrete of that floor. So you also need to consider outriggers and ground. But we'll move away from that at the moment. We're focusing today primarily on articulated vehicles because they are just the worst. It's difficult in some cases to work out what the stability point actually is. And I'm going to use a Franna as an example, a Terex Franna tractor crane. So here's a Franna, typical AT22 pick and carry crane. And it's an articulated vehicle here, booms on the front, counterweights on the back. And one of the things they're smart enough to do is to show two different ratings. Now the darker colour indicates 0 degree articulation, 0 steering, and the lighter colour is the load rating at the maximum steered angle. Now down here it's not much different, but when we get up here it's quite a bit of difference. You know, we're talking about, oh well, at least 400 kilos, 500 kilos in fact, and that can be enough to put a crane over. So in other words, you can pick up at this boom, way out here, 0 pitch, 0 roll. That's another thing to consider. So if we're out here at say 13.5 meter radius, we can pick up 2450 kilos straight ahead. The minute you steer the vehicle to move that load away, your rating has dropped, perhaps as much as 500 kilos. So you need to be very aware of this situation. It's difficult for operators in the heat of working to be able to remember all of these things. But it's not just Franna and crane manufacturers that recognise the problem. Here's a 992 wheel loader, and we're going to zoom in and look at some specifications for it. If I look here, tipping load at maximum operating weight, straight, and then articulated to the maximum. Straight ahead, it's got 62 ton of capability before it tips. Fully articulated, the limit is 10 ton less. And it's even worse when it's on a side grade. So be very careful of tipping loads when steering. Just for fun, I want to show you the importance of understanding where your ballast is and what it's doing. Here's a 3-wheel tractor. Getting down the highway fine because he's got a counterweight in the right position. The caption on this picture is proof man needs a wife. I would agree with that, not necessarily for the same reason, but when you know what your counterweight is doing, you can achieve extreme results. So today we're going to play with some toys. This is an Aveling Barford loader, a rigid framed vehicle. I suspect it was the rear tyres that was steered, but that's our exemplar for rigid frames. This one is an International Payloader 560 and it's articulated. And we're going to start with tipping, and we're going to look at the Aveling Barford. Tipping is an issue if you're carrying too much load, or you're on too big a grade, or you've got your bucket in the wrong position. I want to introduce the concept of a tipping line. It's essentially the line about which the vehicle will pivot. In a loader like this, the tipping line is under the front axle. If you lift too much of a load, the vehicle is going to tip around that tipping line. Simple concept. And my hydraulics have a problem because the bucket's going down. You can tip because you're on a downhill grade carrying too much load, or you're carrying too much load in general. But sometimes, in fact most times, the worst stability point is with the bucket about a metre off the ground. Because of the geometry, it's an arm that curves as it works. It's generally curves to the furthest reach just off the ground. So watch your shovel geometry. It's exactly the same thing here for an articulated vehicle. Carry too much load and you're going to tip over. That's a fairly straightforward thing. You've seen the Ventrac tractor as I've used for examples previously. I've tipped forward 3 or 4 times and nearly been disemboweled on the steering wheel. And all those cases, it's happened when I've changed grade. So I've learnt to keep the bucket very low to the ground. But a rollover is a different situation. When we look at a rigid frame vehicle, we can learn a few things. We talk about keeping the load close to the ground so that it can handle quite a lot of side slope before its center of gravity is on the wrong side of the tipping line. The tipping line is the edge, the outer edge of the tyre contact patch, the point where the vehicle will roll over, the line about which it will roll over. If I have my bucket high, what will happen, and laden, what will happen is the first thing that will get it on the wrong side of the tipping line is the load in the bucket. And it will start to act against the rest of the vehicle. And at some point it will take over. The total center of gravity will get on the wrong side of the vehicle and you're in trouble. exactly the same situation is relevant to articulated vehicles, but they have additional concerns. We saw with the CAT 992 that it had 10 times less stability load when it was steered compared to when it was straight ahead. The reason is that when it's steered, the counterweight has moved so much closer to the front axle. If I put that in a tipping line position, we're straight ahead. Look where the counterweight is. I'll just hold this in place. And now we'll turn it. Look how much closer the counterweight is to the tipping line. So the moment that it encourages stability is essentially counterweight times the distance from the tipping line. By moving that to the steered position, that distance has got much less, and the stabilizing moment has decreased dramatically. You'll also note that the counterweight is well offline with the center line of the bucket. Now let us look at the vehicle on a side slope, tipping sideways. The reason articulated vehicles are generally easier to roll can very quickly be seen here. If I steer this thing, keeping the tyres on the tipping line, the centre line of the bucket and the centre line of the counterweight have suddenly got very close to the tipping line. It won't take much angle to get this thing to roll. Now, it may not be as simple as that. Big machines that lift a long way are very susceptible to being rolled when the bucket is in the air, because it's easier for the center of gravity of the load to get on the wrong side of the tipping line. The reason I had the 992 data at hand is I'd been asked to look at one recently where they picked a bucket. The bucket was actually too big for the machine. It worked fine, but it didn't meet the standards for stability. So generally, all slopes are an issue. Less of an issue for rigid frames. Articulated vehicles on cross slopes are an issue because of the way they steer. And I'm going to try and show this a little differently. Not sure if it'll work. I'll tip up my whiteboard. That's a big problem. Counterweight and load CGs very close to the tipping line. Much more liable to tip over. However, if it's like that, less likely to tip over, because we've just moved the counterweight and the load away from the tipping line. Very difficult to train operators to teach people this, that if they turn up a slope, they're more stable than if they turn down it. This is the sort of three-dimensional geometry that you have to consider when you're designing it. It's also the reason that a low CG is important. That's why counterweights are low on the chassis and not up high. So the higher they are, the more they move laterally on side slopes. So let's return to that 992 at an open cut that I used as an example earlier. And let's just pretend this payloader is that 992. There are several things the operator could have done. What he did do was reduce the size of the bucket, because that was simpler for him. He could have also increased the amount of counterweight at the back, or ballasted the tyres, water or calcium carbonate. It is actually a complicated problem to analyse these vehicles for stability. unless you're the OEM, you don't know the actual height of the centre of gravity of both halves of the machine, and that's what's necessary to do the full analysis. So essentially we analyse it on the flat, straight ahead, and steered, and then basically tell everybody to be careful. Problems arise with potholes and rocks. They can both be quite dangerous, particularly if they coincide. A lot of articulated vehicles do have a roll capability built into their articulated joint. And what that means is that the whole mass of the loader is not directly resisting a rollover. It is quite possible for the front half of the machine to roll and take the rest of the machine with it. So any analysis to standards are in pretty much ideal conditions, and the operators need to be aware of the downside. As a designer, you also need to be aware so that you are encouraging your operators not to run into those troubles and to minimise the risk in the machine design. Remember, once tipping or rolling starts, there's nothing to stop it. It will perpetuate. So you need to stay away from a tipping situation, because once you're in it, you're in deep trouble. Well, we're back on the farm again, this time looking at stability. The Ventrac is an ideal opportunity, a great example to see an articulated vehicle stability issues in real life. What I've done is tape a bit of PVC tube to the center line of the front chassis. It's taped to the grapple, but it's on the center line. And back here is a pendulum, and that's set just above the rear counterweights. You'll see them shortly, but they're just there, and they're the typical cast tractor counterweights. I want you to notice how far they move from their original position when we steer. So I'm going to steer it, and then we'll move the camera around so you can have a better view. So we've just repositioned the camera because we're looking at it tipping around the front axle. So we needed to be on line with the front axle. Here is the pendulum. It's moved forwards about 60 millimeters, about that much. Not a great deal, bearing in mind this is a very small tractor. Where you're going to notice the difference is looking from this direction. Stand by. Okay, things never go quite the way they should. Here's the pendulum. It might be behind this beam, but there it is there. It was here, directly above these counterweights. Look how far it has moved off the center line of the vehicle. This is the big problem of articulated vehicles on side slopes. As soon as they steer, they lose a lot of their roll stability. If you imagine this vehicle on a side slope, but going up the hill, turning up the hill, that might not be a problem because the counterweights are higher. But if the hill went up to my right, and they are now on the low side, you've lost a lot of stability. The previous shot was from the side, showed you lost a little bit of stability longitudinally by steering. It had moved forward, the counterweight center of gravity had moved forward 60 millimeters. This movement is, let's have a look. Over 400. And this is a small machine. Imagine what it was like on a Caterpillar 992, a huge machine. The effect is amplified. Admittedly, that machine is bigger, Physically, it's wider and therefore more stable in some ways. But this is the issue that you face all the time when you turn an articulated vehicle. Instead of the center of gravity of the counterweight being here, it's now over here. And that's a problem in many conditions. So if you're serious about this, about making sure your vehicle is stable, or perhaps it's going to operate in awkward conditions, there are ways to test it. You can use a tilt table, or you can even use just a pair of winches. Let's have a look at a few pictures. This rather scary looking image is not something I'd recommend. Obviously there's some winch ropes here rolling the vehicle over. Very faintly there is a winch rope here restraining it from going too far over. I'm amazed these tyres are in a good condition. I'm surprised they haven't distorted dramatically. But there's a rough and ready way of doing things. I'm not sure I'd recommend it. This is more like the recommended way. This is a professional tilt table. This particular vehicle happens to have tracks. It's a rural fire service truck. I want to show you this. See this bit of angle along the tilt table. You'll find every tilt table has something like that. Because long before the vehicle tips, it will slide. And the only way to stop it sliding is to have a buffer against which the tyres, or in this case the tracks, rest. You can use tilt tables for all sorts of things. Obviously a big combination here, and you'll notice that the wheels on each bogie are restrained laterally. This image shows an underground loader, really a tool carrier, being tested using a piece of fabrication that was basically in the backyard. We were able to put a crane on that. The structure was strong enough to withstand the loadings, and we were able to use the crane to tilt it. You'll see a big concrete block. The vehicle is steered, so this is in its worst condition. The other side of the vehicle is chained to the platform so that it won't roll right over. Now, in this series of tests, I actually had to put a stop to it because the original tyres were foam filled and were distorting so horrendously down here that we were concerned about a catastrophic failure. We switched to pneumatic tyres, pumped them right up, and were able to get tilt table results. One of the issues with tilting articulated vehicles in their steered condition is you need to be very careful that the load doesn't get on the wrong side of the axis of the tilt table. I've had a couple of occasions using tilt tables where I was concerned that the whole thing, not just the vehicle and the table were going to tip. So you need to be careful of that. Now, I've always had my doubts about tilt table testing. It does give you a measure of stability, but it's an unrealistic measure of stability because the vehicle will always slide before it tilts. The military in particular is very, very fond of tilt table testing and use it as some sort of measure, but you'll end up with the thing being stable on such an angle that you'd never drive across it, and you physically couldn't because you'd slide down the hill. So to me, tilt table tests are a good indication, but they're not the ultimate goal. The ultimate goal is a vehicle on a track doing its job. So that's a lot of detail about rollover. It affects your steering, perhaps your bucket capacity, suspension design, counterweights, tyre ballast. There's a lot of issues to be considered. You may, if it's a crane, an elevating work platform, a telehandler, You may decide to avoid the whole issue by interlocking with the stabilizers so that the unit can't reach out unless the stabilizers are down. There are various ways of treating the problem of rollover, but they need to be considered. Always, potholes and rocks and flat tyres. You may think they're minor issues, but they're not if they happen to you. Remember, once something starts to tip or roll, it's gone. There's nothing to keep it back. All these tilt tables have a chain to stop the vehicle going very far at all. Chain's loose, and the way you know that the vehicle has actually tipped is it suddenly goes taut. The vehicle doesn't actually roll off the table. So you need to consider it. You might need to test it to be absolutely sure, but be damn sure, put it to bed, and move on comfortably to the next stage of the design.